about you, but I hate when I run a PCR reaction and then I go and check the gel and I see multiple bands instead of that one nice band that I want to see representing my amplified product of interest. But don't worry, there are things that you can do to increase the specificity of your PCR reaction. It might be a pain to optimize and troubleshoot, but it is possible. So some of these methods include redesigning your primers to make them more specific, such as by making them longer so they're less likely to bind to other sites, as well as to make them so that you avoid any primer dimers and structures and things like this forming. Other things involve making changes just to the PCR reaction conditions, such as changing concentrations, or most commonly where I start is actually by changing the annealing temperature. And so I'll tell you more about all of these. Let's start with the stuff that you can do with your PCR reaction so that you don't have to actually go back and design your primers and order more primers, because no one wants to do that, right? So the annealing temperature, we'll start there because that's kind of like the most crucial. Basically, the annealing temperature is the temperature at which you set the PCR machine for when you want the primers to bind. So each cycle of PCR, you have the strands come apart, you have the anneal step, so that's the melt step. You have the anneal step where the primer binds, then you have the extension step where the polymerase goes to work copying the DNA. Now, during that annealing step, what's going to happen is that the primers have to go and they have to find the site to bind to and bind to that site. If you're having non-specific products, what's happening is that primer's finding multiple sites. Or it can also be that the primer's finding the right site, but it's not getting all the way through because you didn't put your extension time long enough or something like this. But we're just going to assume that right now, basically what's happening is your primer is finding other sites to bind to, and it doesn't like unbind to them. So basically your primer doesn't like have honing in skills on the site that you want. What's happening is that the primer is just basically going to sample these sites along the DNA, and if it happens to bind to something that it has like perfect complementarity to, so it kind of like matches completely, it can base pair with it, what's going to happen is it's then going to get stuck, because it's not going to have the energy to break free from those interactions and go and find another site. Now, if it has more energy, if you have a higher heat, it's going to be able to potentially break free from those interactions. So that's why it can break free from the weaker interactions. It takes less energy in order to break off those attractions. But what happens is if you design your primer so that it's really, it has a high affinity for the site that you want, then it's going to get stuck there and it's not going to come off. But of course, if you will raise the temperature even further, then eventually it would come off. The TM is the melting temperature. This is the temperature at which it's predicted that like half of the primer is going to be bound to the DNA sequence and half of it would be free. Basically, this is going to dictate what temperature you set the annealing temperature at. Typically, depending on what polymerase you're using and what conditions you're using, it'll be somewhere around that TM. Some protocols have you do it a little below the TM. Some protocols have you do it a little bit above the TM. So use like a calculator for the various polymerase that you're using, such as like NEB has like a tool for the fusion, which is the polymerase that I use. So when you set this temperature, TM though, it's kind of just like a prediction. And so you set it for something in your initial run, and then you might have to then go back and optimize it afterwards. Now think about what's going to happen. If you increase the annealing temperature, you're going to make it so that it's harder for molecules, the primers, to stay bound. And you might think, okay, well that's going to reduce my efficiency, right? I'm not going to make as many copies. But what's going to happen is that if you have a lower annealing temperature, well now it's going to get stuck on those sites that weren't those really specific sites. It's going to not have the energy to break free from those sites. And so the lower your annealing temperature, the higher the risk of having these non-specific binding events and having these non-specific products form. And so basically, if you raise the annealing temperature, now you're decreasing the amount of that non-specific stuff increasing the amount of your specific stuff, assuming that your specific stuff is the thing with the highest TM, like with the highest affinity within your plasmid or within whatever template you have, which is why it's really important that you design those primers well, and we'll get to that in a minute. But the first thing you want to try if you see non-specific bands is try increasing the annealing temperature. Now, if you have a high annealing temperature, sometimes what you can do is you can just skip that annealing step. So say your annealing temperature, like your predicted annealing temperature, or maybe not even the predicted one, but you found that when you do the predicted one, you get non-specific products, so you're like, okay, I'll raise the predicted one. And sometimes what happens is that you raise it and basically you don't have an annealing temperature. Your annealing temperature is the same as your extension temperature or something like this. You can just do a two-step PCR, so skip that anneal step, go straight from the melt step to the extension step, and then, yeah, you can just do, so we call it like a two-step PCR. Now, so that might increase your specificity, but remember that if you have a higher anneal temperature, basically it's going to, not all of the molecules of a primer are going to be able to stay stuck. And so the TM, remember, is the temperature at which half of the duplexes, so the primer templates duplexes, half of them would be stable. And so if you have if you're higher than the TM, basically a lot of your primer isn't going to be able to bind, and so you are going to get that lower efficiency. So there's a method called touchdown PCR, where what it does is it starts the first cycles, it starts with a higher TM, and then in subsequent cycles it lowers the TM. It starts with a higher annealing temperature, and then in subsequent cycles it lowers that annealing temperature. Now what this is going to do is it means that in that first cycle, where basically you're setting the scene for what's going to be amplified, because remember, each cycle of PCR, you're amplifying what you already amplified typically, and so you're making a copy of those things that you copied. And so if that first copy you make is going to be really specific, then it's going to kind of swamp out the copies for the later cycles. Like the later cycles are all going to, or not all, but they're going to be a larger proportion than that non-specific product that you might get, say, in that second cycle if you get some mispriming. So by having your beginning templates that get copied be the right ones, then you can be a little laxer with your annealing temperature in the later steps, because if you have one of those non-specific products form, then it's going to represent a smaller proportion of your final product, because your like good ones got a head start. And so if you lower that annealing temperature in the future cycles, now you make it more likely that you can have more primer bind. And if you have more primer bound, then you can have a greater yield at the end. But by starting with that high temperature, you're able to get that better specificity as well. Something else that can help with specificity and that involves like heat and stuff, is hot start PCR. Basically, this is a polymerase that's kind of like blocked until it gets heated. So when you're setting up your PCR reaction, if you're not using a hot start polymerase, what can happen is that the primers, you can get like primers binding to non-specific sites, and then if the polymerase is able to be active at that lower temperature, even if it's not like its ideal temperature, maybe it can still start going. And it can start going and start making those non-specific products, and then you have a bunch of non-specific products going into your reaction. And remember, we just said that those beginning products are really important. And so you don't want that to happen. And so a hot start polymerase basically has some sort of blocking group or something like this, where basically not until it heats up is it going to become active. But so you can set it up at room temperature or on ice or whatever you want. When you go and you stick it into the cycler, now it heats up. Now the polymerase becomes activated, and you can get your products going and all that stuff, but you don't have to worry about having those lower temperatures where you have the primers binding to those non-specific sites and the polymerase being active at the same time. So hot start PCR is really helpful for that. Okay, so that was things that we're dealing with the temperature. And sometimes you don't know what the good temperature is going to be, because remember, those TM predictors are just predictors. It's also going to depend on things like salt concentrations and various concentrations of things like this in your tube, the polymerase. All this stuff is going to impact what the ideal annealing temperature is. So if you run your reaction and you find that you get some non-specific products, you might say, okay, well, let's try raising that anneal temperature, but how much? So, and if you think about a thermal cycler, you don't want to set up like a single reaction in like 5 different times so that you can have 5 different temperatures to test. Thankfully, PCR machines often can do like a gradient where it'll have like a temperature gradient, so you can set the range that you want to test, and it'll test basically at like the top, it'll have some temperature, and then it'll go down and down and down to a bottom temperature, or the vice versa, depending on how you're looking at your PCR machine. But basically, the different tubes are going to have a different temperature. And then you can go and you can run a gel of all those temperatures and see which one worked the best. And so you should see that the higher temperature, well, you might, if it's too high, you might not get any products because that primer can't stay bound. But as you go down, then you should be able to see a strong band for your product. And as you go down further, then you should also be starting to see bands for the smaller products. And so you want to find that temperature that's right for your thing. And so the gradient PCR is helpful for this. So I've done that several times and it's worked out well. Okay, so what else can you change in your PCR reaction? And then we'll look at what you can change in your primers. So in the PCR reaction, one easy thing that you can do is just add an additive. So this is commonly something like DMSO. What DMSO does is it basically can disrupt those hydrogen bonding, so the base pairing and things like this, disrupt secondary structures, so the DNA being all folded up. This is going to make it easier for the primer to find the sites that you want. If the sites that you want are hidden, well, now all it's going to do is be able to find those non-specific sites. But if you have your sites unhidden and exposed, well, now the primer can go and it can bind. And so by adding an additive like DMSO, you can be able to help, especially if you have like high GC content templates. Okay, so that was the additive, and we talked about the temperature. Now let's talk about concentrations. One thing that you can do to increase your specificity is to decrease the concentration of either your template or your primers. So the more of the template there is, the more of those non-specific sites that there are all hanging around for the primer to find. The more primer copies there are, the more places, like if all the right sites get used up, then the primer can find the wrong sites and things like this. So basically, if you have too high of concentrations, you can get a decrease in your specificity. So although it might be tempting to try to increase those concentrations, increase your efficiency, you're also going, or your yield, you're going to decrease the specificity if you were to do so. And so I talked about yesterday how if you want to have a higher yield, you want to get more product, it's better to do multiple reactions so you can make a bigger volume, split it up into multiple tubes, and then pull those together at the end, and that'll give you more of your PCR product without having the problem of the decrease in your specificity. One thing to remember though is that basically often it gives like a range of concentrations, like in nanograms per microliter or nanograms. You have to remember that your template, the site of where the primer binds, is just like one site on your template. And if your template's really, really big, well, that means that it's going to take a lot of mass to have one single site. Whereas if you have a small template that you're starting with, maybe you're starting with like a PCR product or something like this, well, now you have the one site is going to correspond to a smaller mass. So if you have the same mass of a bigger template, like genomic DNA or something, you're going to have need a big mass to have the same amount of sites as if you had a smaller part. So if you have a big thing, you're going to need to be in the higher range of that concentration. And then if you have a small site, or a small piece, you're gonna need to be, or not a small piece, but if you have a small template, you're gonna need to be on the lower side. And so that's something to keep in mind as well as to what if you're wondering, well, why is there that range and stuff like that? You need to keep that in mind. And sometimes you might want to even convert to molarity or something like that in terms of the number of sites. So those were some things that you could do to try to increase the specificity of your PCR reaction by changing the reaction conditions. But what you can also do is change your primer. And so, although this means, yes, you have to design a new primer and you have to order a new primer, if you're not having luck with the other optimization methods, this can be a good bet to go to. Things that you can also make sure that when you're designing your primers in the first place, you make them ideal for this. So we talked about the annealing temperature and how we could adjust the annealing temperature and how that was related to the temperature, the melting temperature, the TM. Now the TM is going to depend on things like the GC content. So the GC rich sequences are going to increase your TM, as well as the length. So basically, the longer it is and the more GC there is, the higher the melting temperature is going to be, and the higher your anneal temperature is then going to be. This is because, remember, that TM is representing the temperature at which like half of the duplex is stably stuck together. And if you have stronger interactions, stronger attractions between them, then it's going to be harder to unstick. You're going to get a higher TM. You're going to have to raise the temperature further for the molecules to have enough energy to break free from those attractions. Now, if you have a longer sequence, what's going to happen is that even if like part of it starts to come off, well, now you have all this still stuck there, and you basically get this avidity effect where it's kind of like anchored down, and so it can't go too far without getting pulled back in. It's like it has a really high local concentration because it can't go too far away. And so the longer your binding sequence is, the higher the TM is going to be, and therefore the higher your annealing temperature can be. And if your annealing temperature is higher, well, then what's going to happen is that you're going to be able to increase your annealing temperature to a point where you don't have to worry about the primer getting stuck on things that are non-specific, because those will have a lower affinity. And so basically, if you design your primer to have a higher TM, this can help with that. Making your primer longer can also, not only does it help the TM, but it can help the specificity, because it's less likely that there's going to be other sites that have that whole sequence match. And so the shorter, that's kind of like why passwords are better if they're longer, because they're going to be harder to like randomly guess. A short sequence is more likely to randomly occur, whereas a longer sequence is less likely to just happen by chance. Especially could be a problem if you're doing something like amplifying from genomic DNA or something like this, where you have a lot of different sequences. If you're doing something from a plasmid, say, there's less chance that there's going to be sites that match, and you can more easily test if there's going to be other sites that have similar matches. But still, the longer it is, the better. And the more pure your starting sample is, the better too. If you're using a plasmid, you might not expect there to be like E. coli genomic DNA in there match into your stuff, but that can also happen if you don't do your mini prep well and things like this. So increase the length, increases the TM, and also increases the specificity by making it harder for it to just like randomly occur. When you're dealing with the TM, though, you need to remember that for each reaction, you're going to have two primers, your forward primer and your reverse primer, and each of those are going to have a TM. And in order to be able to like increase the TM, you need to make sure that you're not optimizing for one primer, but then the other primer is not going to be able to bind because it doesn't have a high enough TM. And so you want to make sure that your TMs are close together, and this way when you're adjusting your annealing temperature, you don't have to worry about like one primer then not being able to anneal at that higher temperature. So if one of your primers has like a higher TM than the other, just go ahead and make that other primer longer. Usually that'll make it so that you can have a matching TMs, or at least within a couple degrees of one another. When you're designing your primers as well, you also want to make sure that you don't have your primers be binding to one another, so forming like primer dimers, or be folding up on themselves, so making like hairpins. What this does is it can basically, not only does it hide your primer from binding to your sequence of interest, so it's like you have a lower concentration of it, but it also can cause like amplification of the primer itself, and so you get these short little products. So if you look at your gel and you see these short little products, those are probably PCR or primer dimers and things like this, products of those primers binding to one another or binding to one of themselves and forming these weird short little products. And so that's not what you want to happen. And there are various software tools that you can use to predict whether this is going to happen. So I use like Amplifix, which is just like this free software you can use. There's also like all sorts of primer design softwares that'll test this sort of thing for you. Whether your primers bind to one another, whether they bind to copies of themselves, whether they fold up on themselves. And remember, this is all just prediction, but you want to make your primers so that they're not predicted to do that. And often what you can do is you can just change the site of where your primer is binding if it's not ideal. So sometimes you have to be binding at a specific site if you're doing some sort of mutagenesis, but if you're just doing some sort of PCR to like qPCR or something like this, you can typically adjust where your primer is binding in order to have a primer that has those characteristics that are better for your reaction, such as a higher TM, less likelihood of forming those non-specific products. So those are just some tips to help you avoid having the situation occur where you go and you check your gel and you see multiple bands. So design your primers better in the first place, or redesign your primers if you see those multiple bands, and adjust your PCR conditions in order to make it so that they're less likely to form during the reaction, even if your primers aren't ideal. So length of those primers, avoid this complexity and secondary structure and dimer formation and all of this stuff. Increase your annealing temperature. Skip it altogether if it's high enough. Try touchdown PCR. Try hot start PCR. And good luck.